Good.
You see it?
Yes. So yeah, the next speaker is Ana Maria from Universidad Central de Venezuela, and she will be talking about exploring the toroidal heterotic landscape. Please go ahead, Ana Maria.
Okay. Hi, everyone, and thanks in advance for your attention. And thanks to the organizer for the opportunity to present this work done in collaboration with Bernardo Freiman, Mariana Graña, Carmen Núñez, and Héctor Parra de Freitas. I will begin with my particular motivation that grew from work with Christoph Meyerhofer. We wanted to study the map between the heterotic on T2 and F theory on K3 at every point in modular space. And let me give you an example with three moduli in which the K3 is given by this equation. The moduli are basically the coefficients A, B, and C. The B can be set to 1 by the scalings. This K3 has E7 and E8 singularities. The heterotic side, we turn on some Wilson lines and get an unbroken group E7 times E8 times E1 cubed. We are left with three moduli, the complex structure, the Kähler modulus, and a parameter beta that depends on the Wilson lines. At special points in the moduli space, there is a gauge group enhancement. In particular, at these values here, the U1 cube is enhanced to SU4. Now, the map between the heterotic moduli and the K3 coefficients is known. It is given in terms of simple modular forms. Concretely, these expressions that are written here. And we evaluated these coefficients numerically at this point of enhancement in the heterotic, substituted back in the equation, and in this way found that the K3 develops an I4 singularity, which corresponds precisely to the SU4 and the heterotic side. And now we knew other examples with no map, and other groups of rank 18 appear. So we wanted to know which groups are possible in the heterotic 22, for that matter, on any tori. And later we also thought about getting the group for the CHL strings, for orbifors that give the CHL strings. And along the way, it became clear to us that these questions are related to the Swampland program applied to supersymmetric theories with 16 supercharges. So in the following, I will be addressing these questions of the possible groups in the different setups and the Swampland connection. So I go to the heterotic on tori, but before a quick reminder of the basics. The heterotic is a hybrid of the superstring and the sonic string. Modular invariance implies that the extra left-moving coordinate must live on a 16-dimensional torus with even self-dual lattice, and there are only two such lattices. One is the sum of two E8 root lattices, and the other is a 16-dimensional lattice, which is the generalization of the E8 root lattice. As soon after the heterotic was constructed, Narain considered the very logical possibility of compactifying also D of the X coordinates. And he found that modular invariance implies that the momenta of the full set of internal coordinates must lie in an even self-dual lattice of symmetry D plus 16, which is known as the Narain lattice. And now there are infinite such lattices. They are obtained applying OD D plus 16 transformations to a reference lattice, which is usually taken to be this one here. And right after the Narain's paper, it was noticed that the new theories he was proposing are really conventional compactifications on tori. The background values of the metric, the field, and the gauge fields, the so-called Wilson lines, are the moduli of this coset that precisely parameterize locally the moduli space. For the local global structure, we need to divide by the duality group. In the following, it will be important to know the form of the vectors in the Narain lattice. These are the momenta that depend on the moduli. And it's convenient to introduce this tensor E and to use its components as moduli together with the Wilson line. Something to keep in mind is that points in the lattice are specified by a set of charges or quantum numbers, namely the windings and the quantized momenta along the torus. And these are integers, and a vector in the E8 times E8 lattice. From now on, I consider only the E8 times E8 theory. A simple example is the circle lattice. Here the moduli, the 17 moduli are the radius and 16 components of the Wilson line, or we can trade the radius by this quantity. The momenta are important, crucial to understand the enhancing of the H group because the corresponding states are massless. So if we look at the condition for zero mass from the right movers, we find that it implies that the momentum, the right momentum, has to be zero, and this gives a very restrictive condition because it involves these integers and this vector on in the root lattice. So in particular for generic moduli E and A, the only solution is that all these quantum numbers are zero. Then if we look at the left movers, we see that for generic moduli, the only possibility is to have one oscillator acting on the vacuum, and there are the spacetime oscillators and D plus 16 internal oscillators. So at generic moduli, the master states organized into the gravity multiplet plus the plus 16 U1 8H multiplets. At special moduli, this abelian group is enhanced. For instance, for these values of the moduli given here, we get this group of rank 16 plus D. So an obvious question is which groups can appear. Okay, and surprisingly, this has not received much attention until recently. I will focus in the case without U1s, in which the group is a product of simple factors or with the maximal rank D plus 16. Something we know is that the group is ADE, and that's because the roots are D plus 16 dimensional left momenta, and they all have to have a length squared 2 to correspond to massless states. So the root lattice of the group, which I will denote L, is an even lattice. And the question to which groups happen is equivalent to which even lattices of signature 0, D plus 16 can be embedded in the Narain lattice. In his TASI lecture notes, Taylor points out that the answer can be found by applying the Coulin's formalism of embedding even lattices into even self-dual lattices. This was done in the K3 context, which is a case equals 2 for this by these mathematicians, and we did it in the heterotic context. So let me try to explain quickly these embeddings in the Narain lattice. The basic lattice data is the discriminant group, which is a portion of the dual of the root lattice divided by the lattice, and the discriminant form that assigns the square of the element to every element in the discriminant group assigns the square. Yeah, then the condition for a lattice of signature 0, D plus 16 to have an embedding in the Narain lattice is that there exists an even lattice that we call T of signature 0, D, such that the lattice data are isomorphic. or L has an overlattice. There is a final lattice that of the same rank that includes L with the isomorphic data with the lattice of signature zero. And L has coincides with the sublattice, the root sublattice of the overlattice. This is a bit complicated. Let me try to give an example. Let's consider the lattice of SU2 plus the lattice, the root lattices of SO32, and see if it can be embedded in the Narain lattice for the simple compactification. In this case, the discriminant group has three SU2 factors, one from the SU2, two from the SO32. And there cannot be a T because one-dimensional T has at most one factor. But in this case, we know that the lattice has an overlattice, and this we know because the discriminant group has an isotropic subgroup where the discriminant form is zero. And in this case, it's a SEP2, which is generated by the spinor class of the SO32. In fact, we knew that the root lattice of SO32 has as overlattice the even circular lattice of 16-dimensional, from the heterotic string. So the lattice L in this case has an overlattice, which is the SU2 root lattice plus this gamma 16. The discriminant group is just SEP2, and now there is one-dimensional lattice with isomorphic data, and this is so this embedding goes. Okay. Something that is important is that something that is important is that the isotropic subgroup, which is the quotient of the overlattice by the lattice, is turns out to be the fundamental group that gives the global structure. And in this example, it is then SU2 times SPin32, which is the covering of SO32, quotiented by SEP2. So question then is in practice, how do we find all these allowed lattice sets of rank D plus 16? One way is to start with all possible ADs of the given rank and check for the cooling condition. This is what was done for D plus 2 by Shimada and Chang. For the simple compactification, there's a simple way based on the extended linking diagram of the Narain lattice. And for compactification to 8 dimensions, we used a set of extended linking diagrams and an exploration algorithm that basically starts with a point in moduli space where we know that there is a lattice of maximal rank, and then we move along the slices of reduced rank, looking for other points with maximal rank, and then we iterate. The way to obtain the embeddings via the extended linking diagram is very simple, but we don't have much time to explain. The result is that the allowed lattices are obtained by deleting 2 nodes in the diagram in such a way that the remaining nodes form a proper linking diagram. For instance, deleting the node 1 and the node 8 prime up here, we will get a linking diagram that you see I'm trying to draw. And it's the linking diagram of SO34. From the remaining nodes, one can read the moduli. In particular, the Wilson lines will be given in terms of fundamental weights of associated to the nodes that are related. One can see that there are many lattices that cannot be embedded. Okay, and here's an example. So in this way, Freiman, Graña, and Núñez obtain all the groups in the circle compactification. Later, we check the Nicolin condition and obtain the lattice data. You see there are 44 altogether. This maximal enhances always happen at the fixed point of T-duality, that is the exchange of winding and momenta. And in all cases, we know the global form of the group because we know the generators of this isotropic subgroup. And here there are some examples. In compactification to 8 dimensions, we also obtain all data, all the possible lattices, the data for the lattice embedding, and all the moduli. So in this case, there are altogether 325 groups, but there are 359 distinct models because in some cases there can be two lattices T and two different global structures, meaning two different spectra. The data for the moduli here is up to dualities because we don't know the form of the fundamental region in this case. We know that we can always find points with this tensor E is the identity, and this means that the B field, the background of B field is 0, and the price to pay is that the Wilson lines will be more complicated. The results agree with the classification of AD types of singular fibers in extremal elliptic K3. These are K3 with the Picard number 20. So now I come to the CHL strings. These are a superstring vacua with 16 supercharges in 10 minus 3 dimensions and a gauge group of rank 3+8. They were first obtained in type 1 strings and later found in the heterotic in the fermionic formulation. In the bosonic formulation, they can be realized in the E8 times E8 heterotic as a Z2 asymmetrical default. The Z2 action is a translation by half a period in one of the compact directions, together with the exchange of the two E8 factors. In terms of the coordinates of the E8 cross E8 torus, the symmetric combination is invariant and the anti-symmetric combination is reflected or fixed of the minus sign. For the asymmetric orbifold, we also need the action on the momenta. For those in the E8 cross E8 part, we also do the composition into symmetric and anti-symmetric. And the anti-symmetric piece picks up the minus sign. In the action, there is an additional phase that comes from the translation by half a period in the one of these compact coordinates. And the effect is that the windings along that coordinate will be half integer in the orbifold twisted sector.
Maria,
so, yes,
you have 5 more minutes.
Oh, okay. So let me review the CHL in 9 dimensions and and introduce the Mikhailov lattice. That is the analog of the Narayan lattice. So now that's the Z2 action imposes that the Wilson line has to be symmetric. The vectors in the lattice one can write in terms of a vector in the E8 lattice as explained here. And it is found that all the states in the orbifold spectrum correspond to a set of charge vectors with components twice the winding, which is always integer, the contact momentum, and this vector in the E8 lattice. And one can show that these vectors span an even circular lattice of symmetry 1,9, and this is the Mikhailov lattice in 9 dimensions. The correspondence of the points in the lattice with the states in the orbifold spectrum is follows from the modular invariant partition function. Just as in the case of the toroidal compactification, the enhancing can be understood from the massless states. now for the left movers, the masses depend on whether one is in the untwisted or the twisted sector. From the right movers, again, there will be a condition that is very restrictive because it involves quantized quantities. From the left movers, looking here, we get this condition, and from there one can show that the cation generators only appear in the twisted sector, and there are only 9 of them because the orbifold projection picks up the invariant oscillators. So a generic moduli, we have a gravity multiplet and 91 gauge multiplets, and there is enhancing at the special moduli. But now there's a novelty that these charge vectors can have norm 2 or 4, and this corresponds to having roots of different lengths. So in principle, non-simply laced groups are possible. And in 9 dimensions, this possibility is killed by the orbifold projection, but it happens in lower dimensions. And in 9 dimensions, the Mikhailov lattice also has an extended linking diagram, and one can obtain all the groups by deleting one node this time in the extended diagram. All these groups are at Kac-Moody level, realized at Kac-Moody level 2. They are all simply connected, and they all happen at the fixed point of T-duality. In lower dimensions, the CHL can be seen as a compactification of the 9-dimensional CHL, and the Mikhailov lattice as a piece that comes from the orbifold of the circle, and has a piece from the remaining compact coordinates, but now it is grayscale. And this implies that this lattice is even, but it's no longer self-equal. There are the states in the lattice, I think, can be put in correspondence with these charge vectors. There will be gauge enhancing when there are extra massless states, that is when these 2 equations have non-trivial solution. And one finds that non-simply laced algebras appear now, for instance, in 8 dimensions, the C type, and in lower dimensions, the B type, and also F4. Using the exploration algorithm, we obtain the groups of maximal rank in the CHL in 8 dimensions. Here, the ADE are realized are at level 2, the C are realized at Kac-Moody level 1. The central charge is always less than 18. Something that is important is that the global form can also be obtained. It was found recently by these authors, and they worked explicitly, for instance, this example. Also, the results match the results from the dual F theory with T3 with frozen singularity. So now I will leave the landscape and enter the swampland.
From now on, you're cutting into question time, Ana Maria.
Sorry?
So 25 minutes are up. So from now on, you're cutting into your question time. If you continue.
Okay. So I will finish soon. So you know about the swampland program and the string universality principle. And the point is that our results give support to this string lamppost principle. I mean, we find that there have been constraints on the supersymmetric QS with 16 supercharges coming from applying swampland conditions on the rank. These are obtained by consistency 1 probe primes, and they are satisfied. The more stringent conditions by other swampland conjectures are satisfied 9 dimensions, but there are the known strings satisfied are only for these ranks. There are also swampland constraints on the type of algebras, and there are satisfies, and there are swampland constraints on the global structure that I don't have time to explain, but they have been verified that they are satisfied, especially this one about the absence of one form anomalies. That was we verified the heterotic and the CHL, and has also been verified recently in the 8-dimensional CHL. So I come to my final remarks. Well, it's just a summary of what we did. And just want to stress, we studied the heterotic on tori and all before the CHL using methods that are based on lattice embeddings. These methods can be extended to lower dimensions, and the results give support to string universality. And there's many open problems that one can try to do. I mean, here's a list, but for the moment, I'm finished.
All right.
Thank you.
Thank you very much, Anna Maria. We have time for one question. Alan?
All right, thanks, Anna Maria. So the E8 level 2, I mean, the E8 model also appears in the Llewellyn, Kawai, Tai, and the Dixon and Harvey classification of string vacuum in 10 dimensions.
Yeah, but it's non-supersymmetric.
Yeah, sorry?
It is non-supersymmetric.
Yeah, I agree. So I just wonder if it might be connected by interpolation with the model that you looked at, like the SO16 and the cos SO16 and the 8 cos E8 that are, can be connected by interpolations.
No, we didn't look, but yeah, it could be.
Okay, thanks. Do you know there's also the paper by Partouche and I think de Vauchier on they studied also sort of, I think toroidal, but maybe using a different slightly different formalism. So the type of gauge groups.
No, I did this paper. I didn't know. If you can send the reference, please. And I have a question for you. I mean, I looked all the time if there was a list of models obtained using the fermionic formulation, and I never found.
I mean, it's so it's 2006 08 194. I mean,
okay.
But I mean, the interesting thing about what they find is that they find that sort of they look at configurations where they also the Cartan generators are from the untwisted sectors are eliminated. So they obtain only the gravitational sector from the untwisted sector, and the rest are sort of are generated in a different way. So I was just wondering if you are sort of covering the same space of.
Well, I mean, I'm not sure if they are also considering compactifications.
I mean, I
with
think
maximal, would have maximal supersymmetry. I mean, 16 supercharges. Yeah,
I mean, from what I'm familiar with, what they do, it should. I mean, I would think that it's similar, but anyway, I mean, it may be a question to try to look into.
Okay, thanks.
Thank you.
Right. In the interest of time, we have to move on. So we thank Anna Maria again.
Okay, thank you.